Can you hear me? Am I audible? Am I audible? Just confirm whether everything is all right or we are good to go. This is the third lecture, and in this session we'll be discussing wave particle duality and uncertainty principle. Good morning, Harry. You did not join yesterday's class. I hope you watched the recording. Anyways, let us start. Okay, we'll be doing one thing. Instead of sending links every day, you can just check it out. Okay, this channel you have already subscribed, so you just go through this channel and that live session will be showing there only. Okay, and if possible I will also share the link, but don't depend on that link. In the last moment I was searching for link and I got late. Anyways, so let us start with wave particle duality. Wave particle duality, what does it mean? Every material object has two aspects. One is the particle aspect, another one is the wave aspect. So this wave particle duality theorem was given by the scientist known as de Broglie. This D is written in small letter, okay, de Broglie. So wave particle duality in classical mechanics, waves and particles are two completely distinct types of physical quantity. In classical world, we perceive them as two entirely different things. Okay, nobody imagined that particle may have some wave properties or wave may have some particle aspect. Waves are continuous and spatially extended. So if you are considering a wave, you can imagine it in this way. So you can see it is continuous and it is extended. Whereas if you consider particles, they are discrete and they have only very little or no spatial extent. For the wave, we can see it is spatially extended, but for the particle they have no or very little spatial extent. However, in quantum mechanics, wave sometimes acts as particle and particle sometimes act as wave. Both traits are involved. So this strange behavior of wave and particle is known as the wave particle duality. Now there are certain evidences for the wave like nature of light. If I consider radiation is mainly perceived as wave in classical mechanics. Now there are some evidence for the wave like nature of light. What is the proof that light is a wave? Phenomena like diffraction, interference, polarization, this supports the wave nature of light. And later on Maxwell give his 4 equations which describe the wave nature of the electromagnetic radiation. Now this is very common thing. Now this one is quite interesting, evidences for the particle like nature of light. This one we do not expect classically, that the light will have some particle like nature, but certain experiment like photoelectric effect experiment, black body radiation, Compton effect, this experiment or effect confirm the particle nature of light. Okay, now with the help of this duality we can easily explain the phenomena of refraction, reflection, interference, diffraction, black body radiation and the photoelectric effect. With the rigid concept of like radiation is only wave, we cannot explain. So classical mechanics cannot completely explain everything. We need to go for quantum mechanics, where every material aspect, every material object is said to have two aspects. Now let us talk about this de Broglie hypothesis. So you understand it qualitatively. Now let's try to understand it quantitatively. So the de Broglie hypothesis of matter waves. According to this hypothesis, just like light, all form of matter, it is not only applicable for light, all form of matter will have dual nature, both wave and particle. Remember this. This is not only valid for light. In fact, it is valid for all form of matter. If you are considering a pen, a chalk, a duster, everything will have two aspects, wave and particle. Now, this wave and particle aspect was first experimentally confirmed by the experiment of Davison and Germer. So in a way, you can say that the Davison-Germer experiment give the experimental footing to this de Broglie hypothesis. Okay. Now, as per de Broglie hypothesis, what we can write as per de Broglie hypothesis, the wavelength is inversely proportional to the momentum. Okay, the wavelength is inversely proportional to the momentum of the particle. Momentum of the particle. And this wavelength is also called de Broglie wavelength. De Broglie wavelength. Now, mathematically, how do we represent? Mathematically, any material object, the corresponding de Broglie wavelength is given by the wavelength associated with the particle is given by the de Broglie relation. What is de Broglie relation? De Broglie relation is given by lambda is equals to h upon p. So, you can write h upon mb, where m is the mass of the particle, b is the velocity of the particle. Good morning, Murli. Now, this is one case. Now, if you consider for relativistic case, for relativistic case, this mass m becomes m is equals to m naught by square root of 1 minus v square by c square. So, we have to use relativistic mass. M naught is the rest mass, and you can say m is the dynamical mass. And v is the velocity of the body. V is the velocity of the body. Now, this lambda is equals to h by p, we can also express it vectorially. How? You know, if I go for the vector form, so we can write 1 upon lambda. Okay, 1 upon lambda is equals to p by h. Now, if I multiply 2 pi on both sides, so it becomes 2 pi by lambda, and this becomes p into 2 pi. So, we can write h by 2 pi. We have just taken the 2 pi on the numerator to the denominator. So, multiplying both sides by 2 pi. So 2 pi by lambda gives you k, and this is p h by 2 pi h cut. So vectorially you can write k is equals to p upon h cut. H cut is a constant, so you don't need to give vector sign. So this k is the wave vector and p is the momentum. So if I take modulus on both sides, this modulus of k will be the wave number k 2 pi by lambda, and modulus of p is the magnitude of the momentum, and h cut is h cut. So this k is equals to p by h cut. This is the vector form, you can say, of the de Broglie relation. So this is also important to note. This is clear. Any question? Now this de Broglie wavelength lambda we need to calculate for different cases. So we are considering few special cases. The first case which you gonna deal with is de Broglie wavelength for a particle of energy E. So let's say we have a material particle of mass m which is moving with some energy E. Okay, let's say it is moving with some velocity v. Then so we can write, if a material particle of mass m is moving with velocity v and possessing energy E, then what you can write? We can write the energy of the particle E is equals to half m v square. Let's say there is no applied potential, then half m v square can be written as p square by 2m. So from this we can write p is equals to square root of twice me. Therefore the de Broglie wavelength becomes, lambda is equals to h by p. So p is equals to square root of twice me. So lambda is equals to h by square root of twice me. So if we have a material particle of energy E, then the corresponding de Broglie wavelength will be h by square root of twice me. So you can imagine it in this way, that this is a particle, it is moving, and while moving it is also bearing some wavelength like thing, and the de Broglie wavelength is h by square root of twice me. So this is the first case. Let's move on to the next case. The second case, de Broglie wavelength for a particle in a gaseous state. Like we have considered the kinetic theory of gases, where we considered that inside a container of gas molecules, ideal gas particles are moving randomly. Okay, so according to kinetic theory of gases, the average energy of the material particle, what is the pure nature of energy of the gas molecule inside a gas container? It is purely kinetic in nature. There is no interaction between the gas molecules as such. So potential energy is zero. The only energy is the kinetic energy. Now according to kinetic theory of gases, average energy of a material particle having an absolute temperature T is given by E is equals to 3 by 2 kT. One particle, it has 3 degrees of freedom, and from the equipartition theorem we know that each degree of freedom takes an energy of half kT. So for a particle, for a gas molecule, if it has 3 degrees of freedom, the total energy will be 3 by 2 kT. Okay, that is why E is equals to 3 by 2 kT. K is equals to this Boltzmann constant, and also we know that E is equals to P square by 2m. We have already seen it from this previous expression also. E equals to P square by 2m. So this energy must be equal to this, right? Therefore P square upon 2m must be equals to 3 by 2 kT, and from this we can get the value of P. P is equals to 2 get cancelled, so square root of thrice m kT. Therefore the de Broglie wavelength for a particle in a gaseous medium, in a gaseous state, becomes simple. We'll use the de Broglie relation. Lambda is equals to h upon p. P is equals to square root of thrice m kT. So lambda is equals to h by square root of thrice m kT. So this is the de Broglie wavelength for a particle in a gaseous state, and this was the de Broglie relation for a particle with energy E. Is there any issue with the live or everything all right? Let's talk about this de Broglie wavelength for an accelerated electron. Is it lagging? Is it still lagging? Is it still lagging, Harry? Or is it okay? So let us talk about the de Broglie wavelength for an accelerated. Think it is lagging. Wait a minute. Okay, now I have restarted. So is it fine now? एक बार confirm करो. Okay, now look, suppose an electron accelerates through a potential difference of with potential difference voltage V. So you can imagine it in this way. So we have applied some potential difference and an electron is accelerated. This is an electron, it is accelerated by the potential, let's say V volt. So the work done by electric field on the electron appears as kinetic energy E is equals to E into V, okay, where E is the electron, and hence the de Broglie wavelength for this electron will be how much? Same, lambda is equals to h by p. So lambda is equals to h by p, h by square root of twice m e. Now what is E? E is the energy acquired by the electron by the application of this potential difference. So it becomes h by square root of twice m e v, right? So if we calculate by putting the value, we can get h equals to, lambda is equals to h 6.6 10 to the power minus 34 divided by square root of twice m. M is the mass of the electron, 9.11, 10 to the power minus 31 kilogram, into E is the electronic charge, 1.6 into 10 to the power minus 19 coulomb, and V is V. V is the potential which we will be applying. So if we calculate it, this will give you around 12.3 by square root of V into 10 to the power minus 10 meters. So 10 to the power 10 meters means angstrom, 12.3 by square root of V angstrom. So this formula you can remember, 12.3 by square root of V angstrom. So if you accelerate an electron under the potential difference of V, then you will get this kind of direct result. So here you can say this V is variable. If I imagine, if I take that V is equals to 100 volt, if V is equals to 100 volts, then what will be the value of lambda? Lambda will be 1.23 angstrom. Now this 1.23 angstrom, you can see that this is of the order of the X-ray wavelength. It means the way X-ray behaves, if we accelerate an electron with 100 volts, the electron will also behave like the X-ray. Look, for what we have used X-ray? We have used X-ray for crystal diffraction, right? We have used X-ray for crystal diffraction, and the wavelength of X-ray is of the order of this around 1 angstrom, you can say. Thus, it is possible to demonstrate the wave-like properties by an electrode of an electron by diffracting it from a crystal. This is because the crystal has an interplanar spacing of the order of X-ray wavelength, and same order of wavelength we are able to generate with the help of accelerated electron. Is it clear? This idea is clear? we can accelerate electron and get that corresponding de Broglie wavelength of the order of the X-ray wavelength. Now X-ray wavelength is useful for crystal diffraction because the interplanetary spacing is of the order of the X-ray wavelength, and with the help of electron we can achieve that wavelength. So electron with electron also electron diffraction is possible. Any question, Harry, Murli, or is there any problem in the stream now? I hope everything is resolved now. Let's talk about the role of Planck's constant. Let's say if Planck constant becomes 0, lambda is equals to h by p. So p is equals to h by lambda. Okay. Now if Planck constant is 0, de Broglie wavelength should also be 0. Okay. If h becomes 0, this de Broglie wavelength will also be 0. So what does it mean? De Broglie wavelength becoming 0 means particles of matter would only exhibit classical aspect. Only particle like nature will be there, no wave like nature. Heisenberg's uncertainty principle would also lose significance in the limit of h cut tends to 0, because Heisenberg uncertainty principle says delta x, delta px is greater equals to h cut by 2. Now if h cut becomes 0, there will be no uncertainty, it will be certain. So Heisenberg's uncertainty principle will also be will also lose its significance if h becomes 0. There would be no indeterminacy, and we could predict both momentum and position with utmost accuracy. So it will behave purely classically. Let's try to solve this problem. Estimate the velocity and kinetic energy in electron volt of neutrons required for the study of neutron diffraction in a crystal with interatomic spacing 2 angstrom. Given mass of neutron is equals to this, h value 1 electron volt, everything is given to you. Can you do this problem? You have to find out the velocity and kinetic energy of neutrons for the study of neutron diffraction. Velocity you can easily calculate. Velocity, how will you calculate velocity? Lambda is equals to h by p. So v is, lambda is equals to h by mb. So from that v is equals to h by m lambda. Now once v is calculated, you can easily calculate the kinetic energy by using the formula of half m v square. Give it a try quickly. What is the answer? Using de Broglie relation, V is equals to h by m lambda, because lambda is equals to h by mb. So you can put the value of h 6.626 10 to the power minus 34 joule second. Mass of neutron is given 1.6749 10 to the power minus 27 kilogram into lambda. What is lambda? Interplanar spacing, you know, interplanar spacing becomes of the order of lambda, right? So it is 2 angstrom. So 2 into 10 to the power minus 10 meters. 1 angstrom, we know, 10 to the power minus 10 meters. So if you put all these values, what will you obtain? You will obtain 1.978 into 10 to the power 3 meter per second. Okay, this is the de Broglie. Using the de Broglie relation, we can find out the velocity. Now if you want to calculate kinetic energy, then simply you will use half mv square. Therefore the kinetic energy, let's say T is equals to half mv square, right? So half mv square, let's put the value. This is equals to half mass of the neutron 1.6749 10 to the power minus 27 into velocity 1.978 10 to the power 3 meter per second square. So if you calculate it, you will get it around 3.2765 10 to the power minus 21 joule. Now if you want to calculate it in electron volt, we have to divide by the charge of an electron 1.6 10 to the power minus 19, and this joule will become electron volt. And if you calculate, you will get 20.478 into 10 to the power minus 3 electron volt. So 10 to the power minus 3 electron volt is milli electron volt. So 20.478 milli electron volt. So this is matching with option 2. Okay, is it fine? Let's talk about uncertainty principle. So as per uncertainty principle, we know that delta x delta px is equals to h cut by 2. That is one form, but there is some general uncertainty relation as well. So if you want to express this uncertainty relation, you can express it in this way, that it is impossible. Look, position and momentum, that is just a special case. Generally we can give the theorem in this way: it is impossible to determine two canonical variable simultaneously. Canonical variable, one may be position, then the corresponding conjugated canonical variable will be momentum. If you considering angle, then the corresponding conjugate variable will be angular momentum. Okay, so it is impossible to determine two canonical variables simultaneously for microscopic particle. Let's say if q, so this is a position coordinate, and let's say the corresponding momentum p of q are two canonical variables, then we can write that delta q, delta pq is greater or equals to h cut by 2. Okay, now you can take q something, then correspondingly pq will be decided. So what is this delta q? Delta q is the uncertainty or the error in measurement. Error in measurement of q, and delta p of q, this is the error in measurement of pq. And h cut you already know, h cut is Planck's constant, reduced Planck's constant. This is known as reduced Planck's constant. Now by taking different q's and different pq, we can get several uncertainty relations. So these are some important uncertainty relation. So whenever we talk about uncertainty relations, we generally take this position uncertainty, but other than the position uncertainty, we have few other uncertainty relations as well. So firstly, we'll be talking about the position momentum. So delta x, delta px is greater equals to h cut by 2. X is the position, px is the momentum along x direction, momentum in x direction. The other uncertainty relation is energy time uncertainty relation. This is known as position momentum uncertainty relation. This is known as energy time uncertainty relation. E is the energy, T is the time. Okay. Next one, delta theta. This is angle and angular momentum. Delta theta, delta L, or delta L, delta theta greater equals to h cut by 2, where theta is the angle, L is the angular momentum. Now from the quantum mechanical perspective, these things behaves like operator, like position behaves like operator. We have to consider them in the operator perspective. Px, momentum, is also we have to take them as operator. Okay, energy operator is there. So that is why there is a general uncertainty relation. This is no different than this. This result will come out from the general uncertainty relation as well. So let us talk about this general uncertainty relation. Commutation, you know, like if commutation of AB is equals to AB minus BA, you know it. Okay, so look, just a small information. Let's say this is commutation of AB. So this is AB minus BA, we already know. If this is 0, it means commutes. If it is not equals to 0, it means does not commute. You know it na, Murli, Harry, you know this thing, commute and does not commute. So if two variables commute, you see, if two variables or two operators, if two operators do not commute, in general, one cannot specify both values precisely. Okay. Now let's talk about the general uncertain relation in this perspective. The quantitative measure, the quantitative measure of how the combined uncertainty of measuring two variables relates, just try to understand what it says, relates to their lack of commutativity. Look, if two variables, two operators, let's say A and B, if they commute, then what does it mean? It means we can measure A and B precisely. Now if they do not commute, then A will have some error in measurement, B will also have some error in measurement. So the compensation, we can say, or the result of this lack of commutativity is the error in measurement. This is what it is said. The quantitative measure of how the combined uncertainty of measuring two variables relate to the lack of commutativity. Because they do not commute, there will be uncertainty. If they commute, there will be no uncertainty. You know, commutation of x px is I h cat, so that is not 0. That is why there are uncertainties in measuring x and measuring delta px. So how the combined uncertainty of measuring two variables relates to their lack of commutativity? It is most simply represented as, so this relation you should remember, this is the general uncertainty relation. Let's say if you have two variables, one is A, another one is B. So error in measurement of A will be delta A, error in measurement of B will be delta B. So delta A square, delta B square, if you take the square, it will be greater or equals to 1 by 4 times I commutation of AB square. So this relation you need to remember at any cost. Sometimes it is asked in interviews as well. Delta A square, delta B square greater or equals to 1 by 4 times the expectation value of I of AB square. Why this I is added? To make it real, to make the right hand side real, this I is added. So let us write a remark on this regard, that for AB Hermitian, you know the meaning of Hermitian, I don't need to repeat it. If AB Hermitian, the commutation of AB is anti-Hermitian. Anti-Hermitian just a moment. Anti-Hermitian means there will be I, okay, I will come, and that is why I is multiplied. So I into I will be I square, that is minus 1. So it will become real. If this I was not there, what would happen? This will become imaginary. So to prevent that, because the answer product of uncertainty should be real thing, right? So that is why this I is multiplied. If commutation of AB is anti-Hermitian, so I of AB, this is real. So this is the general uncertainty relation. Anyone has any question based on this uncertainty relation? Now we are going to utilize this general uncertainty relation, and we will see whether we get the other uncertainty relations as well. ये कहाँ पे था? No question? Let's move on. So first of all, we'll be applying this general uncertainty relation. This is a mathematical form of the general uncertainty relation. You have to remember this, okay? Delta A whole square, delta B whole square greater or equals to 1 by 4 expectation value of I of AB. AB is the commutation of AB square. Now let's apply this in minimizing uncertainty for a particle in a 1D box. Particle in 1D box we'll discuss separately in the upcoming lectures. For the timing, you know what is particle in a box. Particle in a box is something like this. So you see there are infinite potentials. So it is forming a well. Now if you place some particle, let's say of mass m, this particle cannot escape the wall because it is bounded by infinite potential well. It is restricted to move inside this well in this line. Maybe this is we can say this is A. This width of the box is A. This is 1D box. 1D infinite potential box. This we'll discuss later. For the time being, you know, to apply the general uncertainty relation, we know we need A and the corresponding momentum B. So minimizing the uncertainty for a particle in 1D box. So here we can denote the position by x and the corresponding momentum of this particle will be denoted by px. So A, so one canonical variable will be x, another canonical variable will be the corresponding momentum, that is px. Now to apply the general uncertainty relation, we know that we need commutation of AB. Okay, so what will be the commutation of AB? Commutation of AB, you know, px, this can be written in the operator form. Px can be written in the operator form in this form, minus I h cut ddx. This is the operator form. In some applications they are using h cut by 2, some application h cut. What is the difference? Very good question, and it is very simple thing, no confusion. H cut by 2 greater equals to h cut by 2. Actually, if the case of a particle in a harmonic oscillator, one dimensional harmonic oscillator was not there, then in general for all the cases we take h cut, okay, for others. And for only for the case of one dimensional harmonic oscillator, 1D harmonic oscillator, we take h cut by 2 because of the 0 point energy, half h cut omega. Because of the 0 point energy, we only take h cut by 2 for the harmonic oscillator. Otherwise, we consider h cut for all other cases. I think after this there will be no confusion. Murli? So AB minus I h cut is constant. A is x, B this ddx minus I square ddx minus AB minus BA. So I square we have taken common, ddx of x. So this becomes I h cut. This term, first term is 0. So we can say that delta A whole square delta B whole square, which is equals to delta x whole square delta px whole square. This is equals to, you know the formula, 1 by 4. What is in the formula? Greater equals to 1 by 4 times I times AB. So I times AB is I times I h cut, then square. So I minus 1 h cut. So it is equals to h cut square by 4. So you can say that delta x delta px is greater equals to h cut by 2. So we are getting back the position uncertainty, position momentum uncertainty relation, isn't it? So this is how we apply the general uncertainty relation. H cut greater than h cut by 2 is h cut by 2 is minimum uncertainty. Yeah. Look, there are several systems. We have a particle in a box. This is one system. Harmonic oscillator, that is another system, and some other systems will also be there. So only for harmonic oscillator, one dimensional harmonic oscillator, the minimum uncertainty is h cut by 2. For other systems, the minimum uncertainty will be h cut. This is what it is. Just remember this one. Only the exception is 1D harmonic oscillator. Let me show you some example, then it will be more clear to you. Let's consider the ground state energy of hydrogen atom. Okay. So we want to calculate the ground state energy of hydrogen atom. If you see hydrogen atom, what it has? It has one proton and one electron. There is no neutron. Okay. Hydrogen atom is 1H1. So it has one proton inside the nucleus and one electron outside. There is no neutron involved. And let's say it is moving in the first orbit, which is known as the Bohr orbit, right? So this distance will be A. A is the Bohr radius. A is Bohr radius, Bohr's radius, or the radius of the first orbit. Okay. So we can write the total energy of the hydrogen atom, the total energy of the electron in hydrogen atom is, let's say, E total. It will be how much? Look, electron is revolving around the nucleus, so it will have kinetic energy, that is p square upon 2m. If I consider that it has mass m, then p square by 2m will be kinetic energy. And you see the potential energy is coming from this Coulomb attraction. Coulomb attraction is 1 by 4 pi epsilon naught q1 q2 by r square. Okay, q1 q2 by r. Actually we are talking about energy, not force. Now this electron is negative, and here we have a proton, so it has charge plus E. So plus minus minus, that is why a minus sign has been added, E square by A. I hope this is clear. Now we can use position momentum uncertainty relation. Position momentum uncertainty relation. So what will you write? Delta x, delta px. Should I write h cut or h cut by 2? Tell me, Murli, Harry, should I write h cut or should I write h cut by 2? We should write h cut because h cut by 2 will only be written in the case of harmonic oscillator, one dimensional harmonic oscillator. For other case, it will be h cut. Now delta x, you know, this is A, delta px approximately h cut. So delta px is h cut by A. So here you see delta px, it is represented by P. Okay, now so delta px is same as P. H cut by A. We can write it in this way. So let's plug in this into the expression of energy for the ground state. E total has to be minimum. Okay, so if you want to make E total minimum, so for this d E total by dA, this must be 0, right? So if you make dE total by dA equals to 0, then what will you get? Okay, first let's put this value, let's plug in this value of P into this expression, because everything we need to convert it in terms of A. So P square by 2m, P is equals to h cut by A, so this becomes h cut square by 2m A square, and this is E square by 4 pi epsilon naught A, right? So d total by dA is equals to 0. It means minus h cut square by m. Let's say this will be 0 at A is equals to A naught. A naught is the Bohr radius, you can say. A naught is the Bohr radius. So don't get confused with A and A naught. Basically they are same for the ground state. So we are writing A naught plus E square by 4 pi epsilon naught A naught square. 1 minus is coming from the derivative, so it is absorbed. So this is equals to 0, and from this we can get the value of A naught to be 4 pi epsilon naught h cut square divided by m E square. Okay, now if you plug in this A naught into the expression of total energy, then we will get the ground state. Therefore E ground state, it is obtained by putting A is equals to A naught in that E total expression. And if you put A is equals to A naught means 4 pi epsilon naught h cut square by m E square into this expression, what will you get? You will get minus m e to the power 4 by 4 pi epsilon naught square times 2 h cut square. So if you put all these values, mass of electron, charge of electron, epsilon naught value, h cut value, everything you will, if you put, you will get to be minus 13.6 electron volt, isn't it? All clear? Tell me so that we can move forward. Ajay is not coming in the class. Let's go for this ground state energy of quantum harmonic oscillator. So if you consider harmonic oscillator, you know the potential, how it looks like. The potential is somewhat looking like this. This is the half kx square type potential, right? V of x versus x. This is the harmonic oscillator potential. So if a particle is moving under this potential, what will be the energy? The energy of a particle moving under the influence of, moving under the 1D harmonic oscillator potential is given by, let's say, a particle of mass m under the 1D harmonic oscillator potential is given by, what will be its value? E is equals to p square by 2m plus half m omega square x square, you can write. Now this is overall the energy. The energy of the quantum harmonic oscillator, say one dimensional quantum harmonic oscillator, must be at least, when we are writing this term must be at least, means we have to written it in this way, delta p whole square by 2m half m omega square delta x. So when we are minimizing, then this px can be represented by the errors delta p delta x or uncertainty. Okay. Now taking the lower limit of the uncertainty relation, using the uncertainty relation, we need to calculate the ground state energy. So uncertainty relation we are using, so here we will be writing delta x delta p x approximately, not h cut but h cut by 2 we will write, because this is the case of harmonic oscillator. So from this we can calculate the value of delta px. Delta px is approximately h cut by 2 delta x. So your E becomes delta p square. So p is equals to delta px So it becomes h cut square, 2 square 4 duguna 8. So 8 m delta x square plus half m omega square delta x square. We don't need to do anything with the second term. Now we have to minimize this. To get the ground state energy, we have to minimize this E. For the ground state energy, what we can write? We can write dE by d delta x. It should be equals to 0, isn't it? What does it give you? Derivative with respect to delta x, so minus 2 minus 3, so minus h cut square by 4 m delta x cube, and the second term, this 2 is cancelling, this is equals to 0. So it means h cut square by 4 m delta x cube is equals to m omega square delta x. So delta x to the power 4 is equals to h cut square by 4 m square omega square. So from this you can write delta x is equals to h cut. So look, delta x square is equals to square root of this, so h cut by 2 m omega. Now further taking square root will give you h cut by twice omega with the square root. So for this we will get the minimum value of the energy. Therefore the ground state energy, let's say E0, this will be E at delta x is equals to root over h cut by twice m omega. Simple thing, है ना? So let's put this value. So we had h cut square by 8m delta x square, h cut square by 8m delta x is this, delta x square means this becomes h cut by twice m omega, right, plus half m omega square delta x square means h cut by twice m omega. So what does it become? This 2m and this 8m gives you 4 h cut, 1 h cut is cancelling, mm cancelling, okay, omega. So h cut omega by 4, the second one is also giving you h cut omega by 4, and you get h cut omega by 2, and this is what we know, the ground state energy of harmonic oscillator. So ground state energy of harmonic oscillator is not zero, it is non-zero. This is known as the 0 point energy. This is known as the 0 point energy. Did you understand how to apply uncertainty relation in several cases? Now this is a very significant physical result because it tells us that the energy of the system described by the harmonic oscillator potential cannot have zero energy. It has some non-zero energy which is known as the 0 point energy. Physical systems such as atoms in solid lattice or in polyatomic molecules in a gas cannot have a zero energy even at absolute zero temperature. Even if you take this system, into absolute zero temperature, it will not have zero energy. The energy of the ground vibrational state is often referred to as 0 point vibration. The 0 point energy is sufficient to prevent liquid helium-4 from freezing at atmospheric pressure, no matter how low the temperature is. Okay, let us take some other examples. Width of the spectral line. In atomic physics, we have read that a spectral line is not a very fine line, but we see a spread. Okay, but we see a spread. This is not a single line. We see some spread. Ideally, it should have been a fine line, but there is a spread. So, width of this spectral lines, how it is explained by the application of uncertainty relation. Let us say atoms remain in the excited states, for a finite time, let us say tau. So, if we consider that there are two states, so what it does, atom stay for a time tau, then it decays, right? The amount of time it stays in the excited state is known as the lifetime, called the lifetime. So, it will stay up for that time, then it will transit before making transition. So, using energy time uncertainty relation, we can relate it. So, using energy time uncertainty relation, what do we get? We can write delta E delta T approximately h cut. So, delta E is h delta nu, and this delta T is tau, h cut equals to h by 2 pi. So, we can see that delta nu is equals to 1 upon 2 pi tau. So, you see, this is not a single frequency, but is frequency spread. If I consider this spectral line, it is a single frequency, but from the uncertainty relation, you see this spread is delta nu. Because this tau is non-zero, it is of the order of 10 to the minus 8 centimeter, sorry, 10 to the minus 8 second. So, 1 by 2 pi tau will be some value, non-zero value. So, if there is some non-zero value, it means there are some spread. If spread is not there, what does it mean? If spread is not there, it means delta nu is equals to 0. But we can see using the uncertainty relation that this spread has some significant value, finite value. That is why this explains the width of the spectral lines. So, for most of the states, tau is of the order of 10 to the power minus 8 second, and because of that delta nu is of the order of 10 to the power approximately is of the order of 10 to the power 8 Hertz. This spreading is experimentally observed when the pressure is very low. Clear? One last case we'll discuss, then we'll wrap up the session. That is the non-existence of electron inside the nucleus. You know, electron resides outside the nucleus. Why can't electron reside inside the nucleus? That can also be explained using the uncertainty relation. So let's talk about this. This is the final one. Non-existence of electron inside the nucleus. So if, for the sake of argument, if we consider that for an electron, why this argument comes? Because you know, for radioactive atom, for some radioactive atoms, we have seen that it emits beta particle, right? Beta particles. So beta particle is nothing but electron. So from this, the question arises whether, because this radioactivity is a nuclear phenomena, means whatever particle like alpha, beta, gamma, whatever this radiation comes, it originates from the nucleus only. So beta ray is basically an electron, right? So from that, the confusion arises whether this electron is part of the nucleus or not. Okay, you understand why you are discussing this non-existence of electron, how it is connected to pressure. So there are several effects. Okay, now we'll talk about it in atomic physics. Actually, some different types of broadening is there. Okay, this is the natural broadening. Natural broadening. Now, if you are considering some gas molecules or gas, this spectral line, let's say for sodium gas line, okay, na? With sodium light, we observe this spectral line, right? So it must be contained in some gas. So some pressure will be there. Now this broadening can be originated by different methods. This delta nu which you got, this is known as the natural broadening. Other than the natural broadening, because of the relative motion of the different particle inside the gas, there will be some broadening. Some Doppler broadening is there. Some broadening due to pressure is also there. Okay. So those things are there. So don't worry about this last line. For the timing, you just focus on this. This broadening thing we can discuss in the atomic class. Look, for an electron to exist inside a nucleus, the uncertainty in its position must be at least of the order of 2 times R naught. If I consider, let's say this is the nucleus. Okay, this is the nucleus. So it has a radius, let's say this is R naught. So this becomes 2 times R naught. So using position momentum uncertainty, relation, we get delta x delta px is approximately equals to h hat. So delta x will be of the order of this 2 R naught. Okay, and delta p, x is equals to delta p, let's say. So h hat. From this we can get the value of the momentum delta p, h hat by 2 R naught. If you put the value of h hat, it is 1.055 10 to the power minus 34 divided by 2 times R naught. R naught is the radius of the nucleus. Radius of the nucleus, you know, 10 to the power approximately 10 to the power minus 14 meter. So if you calculate this, you will get it around 5.2 28 into 10 to the power minus 21. So momentum, so kg meter per second. Okay. So once you get the momentum, we can calculate the kinetic energy. What is the kinetic energy? Kinetic energy T will be equals to P square by 2m. So P, we have got this. So P square by 2m, by putting the mass of the electron and value of P square this, you will get it around 95.7 mega electron volt. Here we have used for a typical nuclei R0 approximately of the order of 10 to the power minus 14 meter. Now you see, if electron has to exist inside the nucleus, it must have a kinetic, it will have a kinetic energy of 95.7 MeV. But the beta particle which you see, it is only emitted with few MeV, so which contradicts. Okay, from our calculation, if we just assume that electron is existing inside the nucleus, so by assuming that, we should have got the kinetic energy of the order of 95.7 MeV. But in actual scenario, we see that the beta particle or the electron has the kinetic energy of few mega electron volt, maybe 1 or 2 mega electron volt. So there is a wide difference. So that explains that electron cannot reside inside the nucleus. Okay. In beta decay, the energy of the emitted electrons is usually of the order of a few MeV, 4 MeV to 9 MeV. That is for, I think, alpha particle, no? Yeah, yes, you can say it is less than 10 MeV, and here it is 100 MeV. So we can, like, if we had if beta particle had an energy of, let's say, 80 to 90 MeV, then we can say that okay, it is a part of the nucleus. But less than 10 MeV and 100, around 100 MeV, there is a no match, right? Therefore, one does not expect the electron to be a constituent of the nucleus. So with this lecture is over. If you have any question till now, you can ask Harry, Murli. No question? If there is no question, then let's end the session here. Thank you very much. From the next day onwards, we will start our mathematical tools of quantum mechanics. This is very important. That mathematical tool is the most important. If you understand that, then the upcoming sessions will be very much easy for you. Okay, bye. Take care, guys.